All right, welcome back. So we've got a new idea here where we're finding the areas between two curves. So how does that come into play? So we've got y equals x squared and y equals 2x plus 3. So we know that y equals x squared and 2x plus 3 are linears and quadratics respectively. So we're going to have y equals x, well, it's twice as steep and it's up at 3. So we know that there's going to be a linear like this. Okay, a linear that goes like this. And the second thing we know is that there's a quadratic, and the quadratic is just that general lovely quadratic shape that's going to head up here and shoot up there at some point. And also on this side, symmetrical. So it's going to skip up here beautifully in this direction. And so we get this composite picture of two curves and the area between the curves. So the idea here is that we would have the result of the two curves being, if we take the area of the linear part, now the areas of intersection here are going to define the limits of integration. So we'll come back to that in a moment, but just to stick to this point, we'll have the area under the curve. We'll call that A and B again. A and B. And so an area under the curve is all of that area. Okay? The next thing we'll have is the equivalent area for A and B underneath the quadratic. So it too will have an area. It too will have an area under the curve. When we composite these together, that is, we take the area under the linear and subtract the area under the quadratic, clearly we're going to have our desired shape. Okay, clearly we're going to have that shape. So it's an amalgam of those. Okay, it's a composition of those. So we need to be able to keep this idea together, because this is a clue. This is a hint here, this minus. How do we do this? Well, we subtract two functions. We'll do that more in a moment. But how do I work out these values? This is the y-axis. This one here has a corresponding x value. Okay, some value of x. This one here has a corresponding y value, some value of x. X equals A and x equals B. Now, here's the thing. They both have the same y value. Y is equal to y here. And y is also equal to y here. So that's true. That's a truth. They've both got the same y value for a given x value. They both have the same y value for a given x value. However, we can't compute y equals y. That doesn't make any sense. What we can do, instead of putting y equals y, we can put x squared, the left-hand side. So in effect, this is the left-hand side is equal to the left-hand side. But what we want to point out is the right-hand side at some point is also equal to the right-hand side. So we can write it like this. So what do we do with that? Well, undo. What you do to one side, you do to the other. What you do to one side, you do to the other. So we'll end up with x squared minus 2x minus 3 is equal to 0. Now this is now something that we can solve. This is a quadratic. Yes, it's a composite quadratic made up of those two curves together, and that quadratic will tell us these limits of integration. So now we can go away and do whatever method we want to complete the square and get the values. And I'm going to be annoying in a second because I'm going to do it. I'm going to fill this in because I've made a bit of a fuss about this during the course of the semester. Therefore, when is this true? This is true when x equals whatever the first value is and whatever the second value is. Now, I can think about those values in terms of the shortcuts. What are the roots of minus 3? So it's more likely to be 3 and 1, but we need a plus or minus. So maybe we have a negative 3 and a plus 2, plus 1. So I can guess. I'm guessing based on roots and my knowledge of quadratics. Okay, plus 1, negative 3. Let's check that. X squared minus 3x plus x is minus 2x, tick. Plus 1 times minus 3. So we've found them. Okay, I could go, now when is this true? Well, when x is minus 1 and x is plus 3. So they're our limits of integration. So we're going to take that integral and we're going to go from minus 1 to 3. Okay? Do I have to be completely annoying? Well, I'm Jason, so Jason is a bit like that, isn't he? He's a bit annoying. Why would you make us do this? You just showed us how to do it. I know, but this is bulletproof. It always works, doesn't it? Okay, and so we'll square that. I always leave that vacant, which equals 1, which is our square. So x squared minus 2x plus 1 is a perfect square. In x and negative 1, check it, x squared tick, minus x minus 2x tick, minus times a minus is a plus tick, so we've got that. You can't just willy-nilly add 1, so you have to do a minus. So there's our minus 1. And what about this minus 3? You didn't bring that down, are we? So bring down the minus 3 equal to 0. So minus 3 minus 1 is minus 4 equal to 0. Solving this, we're going to add to 4. What you do to one side, you do to the other. We're going to take the square roots of both sides, undo. So we've got plus or minus the square root of 4, which is plus or minus 2, x minus 1. And then finally we're going to add 1, aren't we? So we're going to add 1 to both sides. So we get x is equal to 1 plus or minus 2, which is going to be 1 plus 2, which is 3, and 1 minus 2, which is negative 1. Now look, they're the same thing. We've actually got the result straight up, so we've found the integrals. I can't encourage you enough to practice your gymnastics. Completing the square, solving by completing the square is what we want at university, particularly if you're going to do 4-unit levels of maths, which you will be. So, yeah, just have to be careful with that, okay? All right, so now we can do the integral of this thing between minus 1 and 3. And that will give us the thing that we want. So up and under. Clearly the 2's will cancel. Minus 1 and 3 by the fundamental theorem. So finally that gives us our scaffolding. And I know it's a drudgery, isn't it? You've got to put them all in. And we've got to go cube that term. You've got to square that term. You've got to multiply by 3 that term. You've got to repeat that whole thing again. Okay, so I think I might have made a comment during the workshop about some genders are very much better at this than others. Just the patience factor and willingness. So just be willing. Okay, just be willing. Get there and do it. 3 3s are 9, 3s are 27. 27 on 3 is 9. 3 3s are 9. 3 3s are 9, it's minus 9. Now this will be an expansion, so be careful. Everything's going to get a minus here. So that's minus a third. Now that was also a minus. This stays. Because that's an odd, this stays. Just be careful. So that's minus minus. So that's plus 1/3 for that first term. Ooh. The square becomes a positive, but it's minus by this, but it's minus, so it's plus. Okay. And this one here is minus times a minus, which is a plus. So it's plus 3, but it's times a minus, so it's Nearly got me. Minus 3. Let's see what we can do. We've got a plus 9 and a minus 9. We've got minus 9 minus 9 minus 3 is minus 12. So we've got 1/3 plus 1/3 minus 11. I'm counting. So we make that 3s. So we get 1 minus 33 over 3, which is negative 32 on 3 units squared. Now, what's happened? Why did I get a negative? Why did this happen? Now, I'm being quite deliberate here because when I populated this quadratic, I just pulled this quadratic from where we did some work previously. And that was very naughty of me. Naughty. I'm going to write naughty. Because I said myself in the introduction, hey mate, what about the minus idea there? So it's all well and good that you found all of the things there, but how about the minus? You better fix this up, okay? So what we're going to do is just change colours, and I'm going to show you the difference. It's not much of a difference, but so we're going to integrate the bigger one, 2x plus 3, minus the smaller one, the x. Is that right? So that's like minusing x squared. Still the same thing. Okay, so it's a little subtle thing. Okay, so instead of being naughty, I should have done this. So if we go through and do it again, what's going to happen? What's going to be the difference? Well, when we come to do our minuses, let's do it. Let's just do it because it's worth it. Okay, you guys are worth it. So we're going to have so they'll cancel. Now what have we got? 2's cancelled, so we've got x, we've got squared plus 3 times. So these are these things, aren't they? Then we've got minus x cubed on 3. Don't you remember me saying something about the cube staying? So this might come out with a slightly different. What's going to happen? Exciting. Now we put minus 1 into here and 3 into here for each of these. So we just populate those in. And negative 1 for those. Let's go through 3 3s are 9. 3 3s are 9. 3 3s are 9, 3s are 27. 27 divided by 3 is 9. Now we've got to do this. Remembering that that is going to stay, but minus and minus will be a plus. That square is minus 1 squared, but because of this expansion, it becomes minus 1. Okay. This one becomes plus or minus minus, but times a minus is plus. Okay. And finally we get this happenstance of minus a cube, minus an odd stays, but because there's a minus, it's going to be a minus times a minus is a plus, but then the expansion minus will pull this back to a minus 1/3. Now how does that differ from what we've got down here? So let's cancel a couple of things. We've got a 9 and a minus 9. Minus 1 plus 3 will be 2. So we'll get 9 plus 2 minus 1/3. Who can tell me what's going to happen? 11. Oh my goodness gracious. 3 over 3 is going to be 33 on 3 minus 1 on 3 is 33 minus 1 on 3, which is 32 on 3 units squared. They are the same except for the minus. So what did we do? We obeyed this rule. Okay? We subtracted. Now, if you do what I did and make your quadratic to find your limits, and you integrate your quadratic and you get a negative, it's not the end of the world, because as you can see clearly it's the same value, just a minus and a plus. Okay, so as long as you keep that in mind when you're going through your processes, that won't be such a big deal. So to formalise that more generally, what we say is that if there's a curve or two curves and we're finding the area between the curves, and one of them is the function of x, which we like to call the function of x, and we had a curve the other day like this, didn't we? A beautiful swoopy quadratic, and we'll call that the f of x. Okay, and if we had another swoopy curve going in the opposite direction, we could almost make one that looked like a mirror image. There'd be nothing wrong with us doing that, and that would be a quadratic, but it would be this quadratic with this cubic with a negative. But in any case, we'd call that g of x. Okay, and if we had 2 points A and B, and we were to find the area between the curves on that interval, okay, then the area would be the difference from A to B for f of x dx. And what's the rule? Minus A to B for g of x. Now, knowing which is positive and which is not, which is greater than which is not, is sometimes itself a trick. Okay, so establish the interval, and that sometimes can be a bit tricky. Okay, if not given. If you can sketch it, if that's helpful. If you're doing homework, you can use Wrk1. If it's in a test, obviously that's a problem. And then the final thing is to do the integrate. Okay, and just notice your output. If it's positive, then clearly you put them the wrong way around. But if it's positive, it's all good. All right, so that brings us to the end of this workshop. This is the great one for this time. This is why you've done Foundation Maths this semester. It's why you came here, to use all of the skills and techniques that have been found today. So please make sure you do those and do them again and again and again until you're comfortable and happy with it. All right, that's enough for this week's workshop. I will see you in next week's workshop. Bye for now.